Welcome everybody to 6.1, which is entitled Projectile Motion. Chapter 6 deals with two-dimensional motion. So I've got just some pictures here I pulled from the internet of projectiles. We've all played Angry Birds before, a classic projectile motion. Doing some image recognition of a projectile. Guy jumping off a high dive. The first thing I took, this is a picture that I use a lot. And it's got a ball that's being fired, and it's got a ball that's being dropped. And I want to look at the ball that's being fired forward. Now, this is what we call a motion diagram, if you remember back from Chapter 1, or Chapter 2, actually. It's a series of pictures taken at equal time intervals. What we're going to do is, first of all, we're going to analyze the motion left and right and the motion up and down. So what I'm going to do is I'm going to place a vertical line in the center of every ball here. Watch what happens. I'll try to do my best to put it right in the center every single time. And you'll see a pattern that emerges as I'm looking at the ball moving forward. And if you take away this picture now, you'll notice that the spacing between all these lines is identical. And this tells us one very important fact. In fact, it's one of the most important facts about projectiles. Number one, they move left and right. Sometimes we call it downrange at a constant speed. It's very important. They move downrange at a constant speed. Next, let's kind of look at how it moves up and down. So I'm going to rotate my line. Try to put a line in the middle of every ball here. Gosh dang it. And let's see if we can see a pattern going on here. Get rid of it. You'll see that they're getting larger as they go down. And that should make sense to you, that they're accelerating down at gravity. So the second really important thing with projectiles, they move up and down, accelerating. And that's completely different than a constant speed. We call this sometimes the independence of motion. Meaning that it moves left and right completely independent of how it moves up and down. And this acceleration, you may have guessed, is 9.80 meters per second squared. And this constant speed is whatever it's fired at. So let me show you a couple of really cool videos that sort of demonstrate these principles. I just pulled them off YouTube. I really like them. This first one I want to show you, this is from a B-52 bomber from inside of its bomb bay. It's going to drop these bombs. And notice how they stay perfectly right below the plane. the bombs move forward at a constant speed as the plane is moving forward at a constant speed. And you see those bombs down there. They're staying at a constant speed until they hit the ground directly below the plane. Isn't that wild? The next one I want to show you, these couple kids, they thought they'd be funny, and they did this, they were playing around with a bowling ball, and they go whizzing down the road, and they fire a bowling ball off a ramp next to their car. So here's the ramp. They're driving probably 35 miles an hour. Whoa! And then this bowling ball, they don't understand that as the car moves downrange, it's probably in cruise control. The bowling ball goes the exact same speed, but there's a crosswind. If you listen carefully, the wind actually blows the ball over on top of the car. Whoa! Boom. Perfect. Moving downrange at a constant velocity. And the last one I wanted to show you is a Mythbuster did this. What they did was they took the question was, if we had a gun that shot at 60 miles an hour and we put it in the back of a truck, and let's say the truck goes 60 miles an hour, so the truck goes forward and we shoot it backwards, what happens? It's a really, really cool video. So they drive this truck going forward at 60 miles an hour. They fire it going backwards at 60 miles an hour with the big potato gun.
I don't know about you guys, but that looked pretty good to me.
It's just amazing. Watch this.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops, and it just falls.
Gravity pulling it straight down. Just amazing, isn't it? Love that stuff. So, what I've got here is projectile motion. Here's a picture of it in its X and Y components, meaning that when you fire something, let's say here's your projectile. It's being fired, and what they're doing is they're looking at the X component of its velocity. You'll notice that its velocity stays constant horizontally. So sometimes I like to break problems horizontally. They move at a constant speed. So a lot of times I just look for the velocity, distance, and time, because you're going to end up using v equals d over t for the horizontal component. Now vertically, it starts out with a small velocity and it grows. It gets bigger and bigger and bigger. So vertically, it has an initial velocity, it has a final velocity, there's an acceleration, a time, and a distance. The acceleration is always going to be 9.80. Now, that'll be positive or negative depending upon which way you assign to be up, positive or negative. And the other thing, and here's the real rabbit in the hat, the thing that links them is time. Whatever this time is going to be the same. The time it takes to go horizontally and the time it takes to go vertically, that's what links these problems. And I'll show you kind of what I mean by this next problem here. I'll take you through exactly what I do, the steps I use to solve a problem like this. So I've got a ball. It's launched at 4.5 meters per second at 66 degrees above the horizontal. So my ball goes like this. I'm initially launching it at 66 degrees above the horizontal with a velocity of 4.5 meters per second. So the first thing I'm going to do is I'm going to break this down into X and Y components, horizontal and vertical. So what I'll do, I will write vertical over here, and then I'll write horizontal over here. And I know vertically it's accelerating. Here I know it's moving at a constant speed. So I could know its velocity, the distance, and the time. Initial velocity, final velocity, acceleration, time, and distance. So these are the things that I could know about this. First of all, it wants to know the height. So I'm looking for a vertical distance. That's the height. And I'm also looking for the time. And remember that maybe these are linked. So let's try this. What I first have to do, because 4.5 meters per second, that's not a vertical velocity, nor is it a horizontal velocity. But what you're going to do is find the components of it. So what I'll do, I'll come over here and I'm going to find the horizontal component of the velocity and the vertical component of the velocity using sine and cosine. So I'll say the sine of 66 degrees is equal to, I'll just call this y, the velocity in the y, Vy over 4.5. So you just pull up your calculator and you take 4.5 times the sine of 66. And you get 4.11. That's my vertical initial velocity, 4.11 meters per second. Now I'll use the cosine to find the velocity in the x. So I'll just call this the velocity in the x over 4.5. So I'll take the cosine of 66. And I'll multiply by 4.5. And I get 1.83. That's the vertical. So I'm going to exploit this spot right here. At that spot, the velocity is 0 vertically. It's not moving up and down. It's only moving left and right. It's still moving to the right at 1.83 meters per second, but it's not going up and it's not going down. I know that the acceleration is negative 9.80. It's negative because I gave that initial velocity a positive number. So because my initial velocity is positive, the acceleration is in the opposite direction. Now I can solve this problem. I can solve it for t. I can also solve it for d. So let's use the equation that doesn't have the letter t in it. Vf squared equals Vi squared plus 2AD. Well, no. Vf equals Vi plus AT. That's the one I want to use. Vf equals Vi plus AT. Final velocity, 0. Initial velocity, 4.11 plus negative 9.80 times the time. So 4.11 divided by 9.8, you get 0.42. 0.42. Now be very, very careful. That's how much time it takes to get right there. It takes 0.42 seconds to get right there. So how much time is it in the air for? You got to double that. Flight time. Equals 0.84 seconds. How high does it go? Let's use an equation that uses distance. So maybe when I want to do, let's make my paper a little bit bigger here. I'll go Vf squared equals Vi squared plus 2AD. You could use the other one. Distance equals VIT plus 1/2 AT squared. You can do that. I just like this one because it's got a 0 in it. Initial velocity, 4.11 squared plus 2 times negative 9.80 times the displacement d. So I take 4.11 and then I square it. and then I divide by 2, and then I divide by 9.8, and I get 0.86. That doesn't seem quite right. I feel like it should go a little higher than that. I just want to check my math again. 4.11, and I'll square it. VF squared equals VI squared plus 2 times A times D. So divided by 2 divided by 9.8, 0.86. Yeah, I guess it seems right. That doesn't seem very high, but man. So how high does it go? It goes 0.86 high. So my steps, how did I come to these answers right here? I broke it down into its X and Y components, and then I used the appropriate equations for the horizontal, and I used the big 3 for the vertical. The time is the key, though. The time is the link. Sometimes the time is the whole time. Sometimes in this case, the time is half the time. You just kind of have to know. Since I use the final velocity, since I'm using this point right here, I know that the time is half of the total time. Now, the last thing I just wanted to share with you is the different types of projectiles. So what I could do, I could have a projectile that I fire straight up in the air, and it comes straight down like this. I could have a projectile that I fire at an angle, so I fire it at an angle. I could have a projectile that I fire completely horizontally. I could also have another projectile that I fire downward at an angle. So I initially shoot it downward at an angle. And then lastly, the final type of projectile I could have is, what if I had a projectile that I fired straight down? All of these different things, the horizontal and vertical components are all kind of similar, and they're all kind of different. What you could say, I'm going to say up is positive in every single case. And in every single case, the acceleration is going to be 9.80 negative. What will be different is the initial velocity. Let's say in every one of these cases I fire it up with a value of 10. In this case, my initial velocity is going to be 10 meters per second. All the way over on the other side, my initial velocity is going to be negative 10. Over here in the very middle, my velocity is going to be vertically 0. I'm not firing it up and down at all. Over here in the middle, I got to figure out the components, the X and Y components. Here I'm firing it forward and down. Let's just say that this comes out to be like 6, and this comes out to be 8. So 6 and 8. So in this case, the vertical velocity in case 2 is going to be 8. In case 3 or 4 over here, it's going to be negative 8. The horizontal is going to be 6, just like the horizontal over here is also going to be 6. In my first cases, case 1, the vertical there is no horizontal velocity given to it at the very beginning. It's only moving up and it's only moving down. Just like over in case 5, the horizontal is also 0. The final velocity. So what you could do, this is where it kind of gets a little bit tricky. Let's say that maybe I know the distance here. Maybe this is 100 meters in all cases. So in all of these, the displacement is going to be, let's maybe use black, -100. Because it's going from here down, so the displacement in all cases it will be -100. Because that's where the final velocity, the final distance, and the initial distance. Now you may realize that some of these are going to be easier to do if you treat down as positive. So in case number 1, I could find all the missing pieces from now. I could use these 3 bits to find my final velocity, to find my time. And the final velocity is going to be the speed with which it hits the ground. I could find the time and go from there. In case number 2, I could do the exact same thing. I could use these 3 pieces to figure out my missing bits, find the distance, because that would be the horizontal distance right here. Case number 3, the exact same thing. From everything horizontally, this is going to be 10. So what I would do, I could figure out this, put that in there, and then solve for the distance if I wanted to. Case 4, same story. It goes on and on. But remember that they're always linked by their time. The time translates back and forth between all different cases.